Okay, let us go to the second exercise of the same exam, the same written exam. Here it is, exercise number 2. And this is the exercise. So first question is state the theorem of existence of zeros. So there are various versions, but the official version that I gave you is the following. So 2.1 is the following. So theorem of existence of zeros. If you have a function from an interval that must be closed and bounded, okay? So a and b cannot be minus infinity or plus infinity. And the function must be continuous. And the sign of f of a or f of b must be different, and so f a times f b must be negative. This is a short way to say that the two signs are one positive and the other negative. It is very important that the function is continuous. Then there exists a point C in the open interval AB, so it cannot be at the boundaries because the product is not equal to 0, such that f of c is equal to 0. This is the statement. So the proof was not asked. Some of you wrote the proof. And the other comments, drawings, and explanations, the graphs and so on, was not asked. So you did not have to say anything about the graph. There were other versions. So, for instance, you can also here add an equal, and then at this point you have to close the interval. Otherwise, it is false. Think of it, but sometimes it was correct. Okay? And you don't need to write here that A and B are finite, because in absence of other specifications, I assume that A and B are finite. So this was easy, also because you can ask Wikipedia. So it is not so complicated. However, at least in reading Wikipedia at that time, you can learn this theorem if you didn't know it before. Second question, which is a bit more critical. Establish and motivate your answer whether the following statement is true. If f from R to R is a monotonically strictly increasing function such that limit here is minus infinity, here plus infinity, then there exists x in R such that f of x is equal to 0. Okay. What was the canonical answer to this question? So 2. Since the limit for x going to plus infinity of f of x I don't write you a canonical, I write you a comment, is equal to plus infinity, this means that there exists an x bar such that f of x bar larger than 0. Analogously, since the other limit f of x is equal to minus infinity, then there exists x tilde such that f of x tilde is less than 0. This is 0 here, 0 here. So by f monotonically increasing, strictly increasing, but strictly here is not necessary, however. Then you have that x tilde is strictly less than x bar. Then one here is tempted to apply Theorem 2.1, but go back to the text. If you go back to the text here, you see that there is a word, a very important word which is missing here, that is continuous. Continuous is missing here. So you can think of it more thorough. Some of you, many of you, quite surprisingly, opted for a comfortable solution. You said monotonically increasing, some of you said monotonically increasing imply continuous. So you can apply the theorem. But this is false. This is enormously false. This is horribly false. Okay, this is false. And so now you can have a doubt. Perhaps it is not true, this statement. Perhaps if we drop the hypothesis of continuity, then we are lost. And what is the only way to see that? The only way is to produce a counterexample. The counterexample must be as simplest as possible. And what is the simplest counterexample here? Consider a line, a chunk of line here, and another chunk of line here. For instance, here -1, here +1. For instance, this can be x minus 1, and this x plus 1. So you have a function f, which is x plus 1, or x larger or equal to 0, x minus 1 for x negative. And of course, this is monotonically increasing and so on, but for every x in R, f of x is different from 0. So the statement is false. Okay. This is for version A and C. For version D and B, the hypothesis of continuity was there. Is among the hypotheses. So let me, or I can show you, for instance, version B. In version B, you have this, you have a continuous function. And in this case, in version B, you just need to, so in that cases, you have that from this reasoning, you just apply the theorem of existence of zeros to f in the interval x tilde x bar. And there you are done. So what are the results that you need? Here, what you use here is the definition of limit. I think none of you invoke definition of limit. Some of you invoke the permanence of sign. This is conceptually right, but it is not really proper because permanence of sign is never referred to infinitely large intervals, but just to finite intervals. Okay? Just to finite limits. So here it is just the definition of limit. However, if you invoke the permanence of sign, for me, it was no problem. I didn't count it as a mistake. What really counted as a mistake is just to tell we apply theorem of existence of zeros to the interval minus infinity plus infinity, because this is not the theorem of existence of zeros. But in the lectures, we already proved this for continuous functions, for cases D and B, as a corollary of the theorem of existence of zeros. So if you invoked the corollary of the existence of zero, for me, it was right. Okay? So is it clear? For A and C, the statement was false, so a counterexample was needed. Some of you avoided the exhibiting a counterexample, but just told me because it is not continuous. Okay, this is a good answer, but it's half of the answer. In mathematics, if you want to convince me, and it won't convince anyone, that a statement is true, you have to prove it. If you want to convince one that a statement is false, you have to exhibit a counterexample. And for D and B, it was just a matter of invoking a corollary that we proved in our lecture, or the definition of limit. But I also accepted the permanence of sign. And then we go to the last question, and the last question was this, and this was basically the same for all versions with small perturbations. No. Something horrible happened. So let me do it. Okay, very good. Oh, here I can make it a bit larger. So the text here is proof that the function f r o r defined by this has at least a critical point in minus pi over 2, 0. First of all, definition of critical point. What is a critical point? A critical point is a point x bar in the domain of f such that f is differentiable at x bar and f prime of x bar is equal to 0. So we don't look here at zeros of the functions, but zeros of the derivative. How can you prove that a derivative is 0? There are basically two ways. First, Rolle theorem, but it doesn't work here. Don't try to force a Rolle, because it is not true that f of 0 is equal to f minus pi over 2. And you immediately see that because here there is an exponential. You know that e to the 0 is equal to 1, but you don't know what is e to the minus pi over 2. This cannot be compensated by any other term. So you have to go to the derivative and then apply the theorem of existence of zeros to the derivative. So here you have f prime is equal to e to the x plus sine of x plus arctangent of x plus x divided by 1 plus x squared minus 1/2 1 plus x squared 2x. So these two terms cancel. So here you have e to the x plus sine of x plus arctangent of x. So here f prime of minus pi over 2 is equal to e to the power minus pi over 2. Sine of minus pi over 2 is equal to minus 1 plus arctangent minus pi over 2. In order to apply the theorem of existence of zeros, you must be able to evaluate the sign of this expression. E to the minus pi over 2 is less than 1. So these two together give a negative contribution, and the arctangent of a negative number is negative. This is not minus infinity. And this is equal to something that we cannot precisely evaluate, but which is less than 0. On the other hand, f prime of 0 is equal to 1 plus 0 plus 0. This is larger than 0. So since f prime is continuous in minus pi over 2, 0, this means that by the theorem of existence of zeros, you have that there exists a c in minus pi over 2 over 0, such that f prime of c is equal to 0, critical point. Very simply. Okay? Quite surprisingly, some of you, many of you, did not evaluate point-wise f prime in minus pi over 2 and 0, but computed the limit. But why? The function is continuous. Why computing a limit? Compute the function directly. This is not a mistake. It's only stupid. Okay? And also some of you also stated the theorem of existence of 0 with the limits here in a and b. Why? Again, it is not a mistake because the function is continuous, but it is incredibly stupid and gives me the idea that you did not understand these results. However, it is not a mistake, so I did not count it a mistake. But it's stupid, so remember. So last thing I want to say, I want to go back to the function because some of you gave me other some other hint on how to prove the function, because when you compute here the slant asymptote, for instance here, f of x is equal to x minus 2 over x minus 2. So go back to the function. Perhaps a smart way to compute the derivative was have f of x, it was here x minus 2 here and x plus 2, and here plus 2 some rest that I do not really remember by heart, and here it was minus 2 and plus 2. Okay, so here it was minus 2 divided x minus 2 plus 2 divided x minus 2. This for x not smaller than 1, and here for x smaller than 1. Okay, this means that the derivative f prime is easily written as 1 plus 2 divided x minus 2 to the square for x larger or equal than 1, and here 1 minus 2 divided by x minus 2 all the square. And of course you immediately see that this is larger than 0, so here you don't have any critical point for x, sorry, not larger than 0, larger than 1. So possible critical points are here, and here to solve this inequality you can simply say that 2 divided by x minus 2 over squared must be equal to 1. So this is that x minus 2 squared minus 2 is equal to 0, and here you immediately have this decomposition, x minus 2 plus square root of 2 and x minus 2 minus square root of 2, and you immediately see that here, since you are bounded by, sorry, I always made a mistake here, you are bounded by x less or equal than 1, the only possibility is this only critical point. It was a smart way of doing computations. Some of you found this way. Okay. On the other hand, some of you, in differentiating the function, so another bad writing, bad in the sense that it is uncomfortable, which means horrible, okay, uncomfortable. So which means horrible, lousy, and disgusting. Some of you used this infamous way of differentiating. So consider this function here. Okay, when you have an absolute value, my suggestion is to unmount the function in the two branches. And but some of you read in some bad books that the derivative of x is equal to x divided by modulus of x. This is true, of course, this is true. I prefer to write it as epsilon of x, which is also called the sine of x. But this is true, but this does not help you at all in doing computations, because it makes you a gift, which is a denominator with absolute value. This is a disgusting gift. You have to refuse this gift. And so you write something like this, f prime of x, and so you write 2. Instead of writing a sign, you write something really sad, and then minus 2x plus 2, and then you have to multiply by 2 minus x, and then plus, and you rewrite this. So this is correct, but it is very heavy for computations, so don't do that. Don't do that. Okay? So I hope that these videos were helpful for you. I suggest you to make comments, not about the video. The video is nice, the video is bad. I really don't appreciate this sort of comments. If you did not understand anything, something, just write it and I will try to answer. Okay? Instead of answering to your emails, because it is really a mess now with your emails, more than 400 emails. So write me your questions and I will answer. Thank you very much.